Repeatedly retrieving stray tennis balls during practice or between matches can be a time-consuming task. Though it may not seem like much in the moment, the time lost to manual ball retrieval accumulates, and valuable playing time is lost. Professional tennis players typically solve this issue by hiring designated ball boys or ball girls to do this work for them. However, for those doing solo practice, especially amateurs, this is not a viable option. A cheaper, more accessible solution is needed for recreational players.
With this in mind, our team has developed a tennis ball retrieving robot. This robot will save players both time and effort by gathering and returning stray tennis balls. A low-cost design makes it affordable to both produce and to purchase, even for those playing tennis casually rather than professionally. Having a battery life of several hours, the tennis ball retriever is well suited to both short bursts of practice and to longer matches. Inbuilt Wi-Fi means that the robot can operate anywhere, and the speed constraints we added ensure that the ball retrieval will not delay the match play. Finally, as the tennis ball retriever is intended to act autonomously, players are able to direct their focus solely on practice and improvement instead of ball retrieval.
For our design, we took a modular approach when modeling pieces to extend the chassis to ensure that all components were able to be held together passively, and that the entire system was easily disassembled for modifications as necessary. The lowest tier of the main body was the only component not attached passively because it needed to be bolted to the chassis. The arms of the capture mechanism were designed to firmly attach the upper and middle tiers, and the induction coil housing played a similar role with the lower and upper tiers. Another intentionally passive component was the capture mechanism itself. This was designed as a lightweight box that hovered approximately a centimeter above the ground to facilitate the desired zero turn radius. The flap on this mechanism was designed to utilize gravity to capture the tennis ball rather than relying on an electrical component that would draw more energy from the client processor, ergo the Raspberry Pi. Although very light, the weight of the capture mechanism was enough to cause a little bit of drooping towards the front of the component. To rectify this issue, rubber bands were attached to the axle of the flap and to the capture mechanism arms. Finally, the gear plate mounts were made to fit snugly on the gear plates that came on the pre-assembled chassis. Snap hooks were implemented to secure the mounts in place, and through holes were carefully placed to fit around the screws that attached the gear plates to the chassis. The shaft protruding from the plate mounts were designed with an arc cut out of the end of the cylindrical part. This arc had a radius equal to that of a typical ping pong ball, as this is where the colored ping pong balls were attached to the robot in order to determine the orientation.
Controlling the robot is a Raspberry Pi 4 Model B+, with an inbuilt Wi-Fi module that allows the Pi to communicate wirelessly with a host network not on board the robot. The Pi also communicates directly with an L293 DNE motor driver IC driving the two DC motors, one mounted on each side to drive the chassis tracks. These motors are capable of rotating both clockwise and counterclockwise, which allows the robot to achieve omnidirectional movement and 360-degree rotation. Two small cooling fans were included in the design to ensure that no components would become overheated. No circuitry was required for the ball capture mechanism, since the final design of this mechanism was passive.
The power source we chose for our robot consisted of two Samsung 35E 18650 lithium-ion batteries. The battery pack consisted of two of these batteries in series with an AMBEST battery management system and protection board, or BMS board for short. This board was selected due to its ability to provide short-circuit protection, overcurrent protection, overcharge protection, and over-discharge protection for the batteries. With the planned onboard charging circuit, this BMS board provided all the protections necessary for reliable power delivery to our robot's components and protected both the batteries and robot from damage. Our battery pack can operate between 6 to 8.4 volts, can output up to 8 amps continuously, and has a battery life of a little over 3 hours when loaded with our design. We envisioned having a charging circuit on board our robot that would provide charging voltage through induction coils. This wireless charger would have allowed for extended battery life and operating time during the course of a tennis game, and would eliminate the need to manually replace the batteries. The intention was to have the robot return to a charging dock after a ball retrieval is completed, where it would await another ball retrieval condition to take place. This charging dock requires an outlet to be plugged into, and operates at 9 volts DC. This 9-volt power supply powers a wireless charging IC module which is connected to an induction transmitter coil. The receiver coil is mounted on the back of the robot, and the receiver IC and charging circuit are located on the lower level of the robot. The receiver coil outputs 5 volts and is connected to a voltage boost regulator, which boosts the output voltage of the coil to 8.4 volts, the rated nominal charging voltage for two 18650 batteries in series. The output of the boost regulator powers the charging circuit, which consists of a BQ2057 WSN charger IC. From here, the charging leads from this circuit are connected to the battery pack. The BQ2057 prevents charging if the battery pack does not meet the charging conditions set by the internal logic of the IC, which protects our robot and power supply from damage.
The method of communication between the controller and robot needed to be designed in such a way that it could be operated without relying on surrounding wireless networks. Our solution to this problem was to have the robot broadcast its own Wi-Fi network, which the controller could connect to, providing a direct link between the two. This approach has several advantages. One, it reduces the latency, as messages do not need to pass through a router or some other wireless access point. Additionally, having the robot broadcast its own network, while it does increase the power cost slightly, allows the system to be much more controller agnostic, because different platforms have different processes for creating networks. Once the network is created by the robot and joined by the controller, the device communicates over low-level TCP sockets. Each communication cycle of the program consists of the controller grabbing a single frame from the camera, performing necessary processing, transmitting movement instructions to the robot, and waiting for the response. Instructions could be sent much faster if the wait for the response step was removed, but keeping this in allows us to make sure that the robot is still connected and that all of the instructions are being processed. Perspective mapping allows for positioning and perspective of the court by the camera to be corrected for. By using this, the camera only needs to be mounted about 10 feet up in the air versus 60 feet in the air if we did not do perspective mapping. There are a few implementations of such an algorithm already out there, however they are designed for small deviations from an orthogonal view and operate on images, not coordinates. It is important for our use case that the algorithm not simply transform the image itself, as that would warp object shapes and severely impede our object detection. Thus we wrote our own perspective mapping algorithm. The algorithm makes one important assumption. The perspective projection of the camera is rectilinear. A rectilinear projection preserves straight lines. If there is a straight line in the real world, the camera will capture and project it as a straight line. This type of projection is extremely common in cameras as it matches how we think of the world. After the user marks out the vertices of the court, the program computes the vanishing point, a property of the rectilinear projection of the two sets of the court's opposite sides. From the distance the object is from each vanishing point in the projection, the algorithm can determine the object's positioning in the world relative to the court-side lengths. Finally, since the court-side lengths are known, the algorithm can determine the object's exact position. There are two objects that we had to detect in our algorithm, the tennis ball and robot. To detect a given object, a color range in the HSV spectrum is supplied. The algorithm begins by masking out everything in the frame that does not fall into that color range. Further filtering is performed that eliminates any regions that are too oblong, too large, or too uncircular. If multiple regions remain, they are scored based on size and circularity, and the region with the highest score is taken to be the object. If no regions remained, the object is assumed to be either obstructed or out of frame. In addition to the robot's position, we also needed the robot's orientation. That is why 4 markers were chosen over a single one. When at least 2 markers are visible, the detection algorithm can determine which direction the robot is facing using the known positions of the markers relative to the robot's origin.
Traditional pathfinding algorithms operate on a lattice of coordinates with different weights attached to each edge or node. We could have segmented the court into a lattice with some small distance between nodes, but this would be vastly inefficient and would only get worse as we demand more precision. This would also require the robot to move directly up, down, left, or right if the lattice was of squares. As such, we designed our own algorithm that is able to take advantage of the characteristics particular to our problem. Specifically, the points in our space cannot take on an arbitrary weight. A point can either be traveled through, or it cannot. Furthermore, our obstacles are given by polygons and as such have easily defined boundaries. These assumptions cannot be made by graph traversal algorithms. Rather than control movement by a series of distinct commands, movement is entirely parameterized by one instruction specifying a velocity and a curvature. Velocity is simply assigned speed, velocity of 1 is full speed forward, a velocity of 0 is still, and a negative velocity moves the robot backward. Curvature is the signed inverse of the turn radius, with positive values turning the robot to its left and negative values turning it to its right. These two parameters provide great flexibility in movement of the robot and allow it to follow any line with any amount of curvature at any speed. There are two primary movement patterns to correct for deviations. The first keeps the robot moving at full speed forward and sets the curvature such that, if kept constant, the robot would move along an arc and intersect with the next checkpoint. The second turns the robot in place to face the robot further towards the checkpoint. It is rare for either of these to be acting alone at any given time. Instead, there is an interpolation parameter that smoothly picks some compromise between the two methods. The GUI is the primary way the user interacts with the system. By dragging the corners of the virtual court to those of the real court as seen in the camera feed, the program creates a one-to-one mapping between the two coordinate systems. Once the mapping is set up, you can click to add obstacles, press the O key to clear them, and press the return key to activate and deactivate the ball retrieval process. When the user is finished, they can press the Q key to quit.
The overall system was able to perform calculations quickly and efficiently. The system can precisely identify the location of the ball and the robot, and then have the robot retrieve the ball autonomously. We concluded that 1 foot per second was an acceptable speed, as the robot would be able to cross the court in 1 minute and 12 seconds. The robot never collided with an obstacle once the system was tuned during testing. This provided empirical evidence that the system would collide with obstacles in less than 1% of the runs. Additionally, the robot was specified to communicate 5 to 10 times per second, and we found that it did better than that metric. It was also able to rotate 360 degrees and travel forward and backwards. The robot's final cost was $381.72, and the robot has a battery life of over 3 hours.